Hello, you all. Darrell Berry Jr. back with some more reading and notes. And I'll have the chat set up momentarily in case some of you all come and drop a line. So that should be the current chat. And what we'll do is continue reading from what we did before. Uh, if you recall, we did the Boltzmann factor, an equation they said we should remember. And the idea is basically if we have a state, and you want the probability of state I, that'll be 1 over z times the exponential negative e to the state I over kt, and z is going to be exponential negative e to the si over kt divided by probability of si, and also e to the negative sj over kt, all divided by ksj. And that seems correct. So apparently we know the energy, well, if we utilize the energy of I, we just need to know the, interesting that we need the probability, but the probability is there. So it's the probability of the other one. So if we want the probability of I, we will use the Z that includes the probability of J. So with a given state, we can find the probability of a different state, as long as one is known. And I guess they're part of the same reservoir system, overall system. So we'll continue with the next section after the last video. It was pretty brief to show the solution of problem 2 because we did that before. And we'll talk about the partition function. Six 6.1 Boltzmann factor. So this is a subsection of 6.1. Partition function. But now you're probably wondering how to calculate Z. Did come to mind. I was looking at that just now about what the Z is related to. The trick is to remember that the total probability of finding the atom in some state or other must be 1. So this deals with normalization. Those who saw some of my quantum mechanics videos, we know that if we have a state of a subatomic particle, we know that the size squared of that state has to be 1. In other words, the particle is going to be located somewhere. So if you integrate the state over all space, that'll give you a probability of 1. And the psi squared dx should be the probability density, if I'm recalling correctly. So this is the probability density. Integrating the probability density over all space gives you the probability of 100%, since the particle is somewhere it exists. So the same idea is going on here, where 1 equals adding up all the states, probabilities of all the states. So that's going to be adding up all the states and the probabilities. We can plug in the partition function. And I'm not sure what they did for this last step. You can see my mouse, it looks like. Let me increase the size of the book a little bit. We have, oh, I see. They just put 1 over z to the outside. Since if you're using z of the opposite state, like we did here, if z is a function of e as a function of sj, and we want si, z, I guess you could also put, this is I, 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 and z is a function of j, and we can move z to the outside and add up all the s's, e to the negative e s over kt, and this is equation 6.9. So we can solve for z. See, and 1 is on the other side there. So we could just say z equals the sum of all the probabilities of s, right, which seems odd. That's the sum of all Boltzmann factors. This sum isn't always easy to carry out, since there may be an infinite number of states S and you may not have a simple formula for their energies. So Z is the sum of all Boltzmann factors. It is quite interesting. Because basically Z is all the other states. It encompasses all the probability of all the other states. Divided by, or dividing the Boltzmann factor of all the other states. Sum isn't always easy to carry out, but the terms in the sum get smaller and smaller as the energies ES get larger, so often you can just compute the first several terms numerically, neglecting states with energies much greater than KT. Right? The quantity Z is called a partition function. So this partition function, and turns out to be far more useful than I would have suspected. It is a constant, in that it does not depend on any particular state S, but it does depend on temperature. All right. To interpret it further, suppose once again that the ground state has energy 0. Then the Boltzmann factor for the ground state is 1. All right. So this is the Boltzmann factor from earlier. If E equals 0, then Boltzmann factor equals e to the 0 equals 1. That's the Boltzmann factor for the ground state. E ground state, Boltzmann factor, ground state. And the rest of the Boltzmann factors are less than 1 by a little or a lot in proportion to the probabilities of the associated states. Okay. Because the Haber value for their energy is more than 0, so it'll end up being 1 divided by e to the something. And the bigger the number, the bigger the dividing, the smaller the Boltzmann factor. Thus, the partition function essentially counts how many states are accessible to the atom, weighing each one in proportion to its probability. At very low temperature, Z is about 1, since all the excited states have small Boltzmann factors. At higher temperature, Z would be much larger. And if we shift all the energies by a constant E0, the whole partition function just gets multiplied by an uninteresting factor of E0, which cancels when we compute probabilities. All right. So I'll move on to the next section. I'll read a few, and we'll just make this one a longer reading section. Thermal excitation of atoms. As a simple application of Boltzmann factors, let's consider a hydrogen atom in the atmosphere of the sun, where the temperature is about 5800 K. We'll see in the following chapter how this temperature can be measured from Earth. I like to compare the probability of finding the atom in one of its first excited states to the probability of finding it in the ground state. The ratio of probabilities is the ratio of Boltzmann factors from our derivation earlier. That was here. The difference in energy is 10.2 electron volts, while kT is 8.62 times 10 to the negative 5 electron volts per Kelvin times 5800 Kelvin, or 0.5 electron volts. So the ratio of probabilities is approximately e to the negative 20.4, or 1.4 times 10 to the negative 9. So it looks like they just have the energies on hand. For every billion atoms in the ground state, roughly 1.4 on average will be in any one of the first excited states. Probability of being in an excited state versus the ground state. So the ratio of probabilities, excited state divided by ground state, is saying is very small. Okay, yeah, that makes sense. For every billion atoms in the ground state, only 1.4 would be in an excited state, so that is very small. Since there are four such excited states, all with the same energy, the total number of atoms in these states will be 4 times as large, about 5.6 for every billion in the ground state. Atoms in the atmosphere of the sun can absorb sunlight on its way toward Earth. Absorb sunlight on its way towards Earth, but only at wavelengths that can induce transitions of the atom into higher excited states. A hydrogen atom in its first excited state can absorb wavelengths in the Balmer series, 656, 486, and 434 nanometers, and so forth. These wavelengths are therefore missing in part from the sunlight we receive. If you put a narrow beam of sunlight through a good diffraction grating, you can see dark lines at the missing wavelengths. Looks like we have a, uh, which one would this be called? Absorption spectrum. There are also other prominent dark lines created by other types of atoms in the solar atmosphere: iron, magnesium, sodium, calcium, and so on. The weird thing is, all these other wavelengths are absorbed by atoms or ions that start out either in the ground state or in very low energy excited states, less than 3 electron volts above the ground state. The Balmer lines, by contrast, come only from the very rare hydrogen atoms that are excited more than 10 electron volts above the ground state. The hydrogen atom in its ground state does not absorb any visible wavelengths, since the Balmer lines are quite prominent among the others. We can only conclude that hydrogen atoms are much more abundant in the sun's atmosphere than any of these other types. Let's read that one more time. The Balmer lines, by contrast, come only from the very rare hydrogen atoms that are excited more than 10 electron volts above the ground state. A hydrogen atom in its ground state does not absorb any visible wavelengths. Since the Balmer lines are quite prominent among the others, we can only conclude that hydrogen atoms are much more abundant in the sun's atmosphere than any of these other types. The recipe of the stars was first worked out by Cecilia Payne in 1924. The story is beautifully told by Philip and Phyllis Morrison in The Ring of Truth. I would like to know more about how we've, of course, I've heard the general idea about Cecilia Payne determining that hydrogen is the bulk of the sun's mass, not a mixture of a bunch of things like was previously thought, but I can use more details on it. So we can see how hydrogen is definitely, at least in this sun gamma UM, photographs of the spectra of two stars. The upper spectra is of a sun-like star in the constellation Cygnus with a surface temperature of about 5800 K. Notice that the hydrogen absorption lines are clearly visible among a number of lines of other elements. The lower spectrum is of a hotter star in Ursa Major, the Big Dipper, with a surface temperature of 9500 K. At this temperature, a much larger fraction of the hydrogen atoms are in their first excited state, so the hydrogen lines are much more prominent than any others. Reproduce with permission from Helma E. Right? Looks like calcium is pretty prominent in the sun-like star. I wonder if I can take the spectra I took of the sun, or sure I can, but I have to find out how to put it in the diagram like this, where I have the spectra taken of the sun, but I have to put them into a sort of the diffraction gradient like image. So I think about how to do that. These are a good bit of problems. All right, so that was the end of 6.1. So I'll take a break. We read the rest of 6.1, and I'll look at some of the problems in a bit. So give me a moment. I'll be back, even about 30 minutes. Take a look at some of the problems from this section. You have a good one.